All right, here's problem number 2 from our exponential functions review. In this one, we're going to do, it's pretty similar to the other one, but what we have to take into account is what we call a percent increase. Okay, so this population of a town is projected to increase by 5% per year, and the current population is 300,000. So when we think about increase by 5%, usually you think, oh, I need to add 5%, right? Which is true, you could do it that way. But what we're looking for is we want to look for something where we don't have to add, we want to multiply, okay? So one of the things we talked about was finding a growth factor, or in your book, they called it a multiplier for a 5% increase, all right? So the idea is I need to take 100% of the population, and I need to add to that 5% of the population, because the 100% is like the population to begin with. So at the end of the year, at the end of each year, I'm going to end up with 105% of what I started with. I'm going to end up with more than what I started with. Okay, so what that means is we need to multiply by 1.05. 1.05 represents 105%. So instead of adding 5%, you'd have to find the original amount plus 5% of that original amount and then add that. We're just going to multiply by 1.05. That gives us the 100% that we started with plus the additional 5%. So the adding is already done. We don't have to worry about that adding. We just multiply by 1.05 and that will give us an increase. Okay, so let's find out what the population is going to be after 1 year. Well, that would be 300,000 times 1.05. And that is going to give us 315,000. Okay. All right. So let's kind of do the same thing we did in problem 1. Let's make a table here. And we're going to have like the years over here. We're going to have the population over here. So this is like 0 years have gone by and the population's 300,000. 1 year goes by and the population is, 315,000. Now you don't have to make a table every time. I'm just trying to explain what's happening here. How do we get from here to here? We multiply by 1.05. Okay. Now if we want the population after 2 years, we'd have to take this number, 315,000, and we'd have to multiply that by 1.05. So let's see what that is really quick. Got my calculator here. So 315,000 times 1.05. All right, so that's 330,750. Okay, now that's not the number we're looking for, but we're just trying to establish a pattern here. The idea is that for every year that goes by, we have to multiply the previous amount by 1.05. So if 3 years have gone by, we're going to have to multiply the original amount by 1.05 3 times. And again, that repeated multiplication is just represented by exponents. Okay, so the idea is, let's say I wanted the population after 3 years. Well, it'd be my initial amount, 300,000. And then I have to multiply it by 1.05 to get here, and then take that amount and multiply that by 1.05, right? And then take that amount and multiply that by 1.05, right? So you see this repeated multiplication by 1.05 over and over and over. Well, that we can just represent as 1.05 to the third. So if we want the population after 3 years, which is not what we're after, but we're just kind of reasoning here, it's going to be 300,000 times 1.05 to the third. Okay, so the idea is if we want the population of the colony after X hours, it's going to be population equals the initial amount, the starting amount, and then it's going to be times 1.05, which is our growth factor, to however many years have gone by. That's going to be the power. Because if 10 years have gone by, we need to multiply by 1.05 10 times, which is the same as 1.05 to the 10th power. So this is our equation here. Okay. Now, if we want the population after 12 years, okay, Okay, well that's going to be 300,000 times 1.05 to the 12th power. Okay, so this is probably going to require a calculator again. It's going to be hard to do off the top of your head, but it comes out to be about 538,756. Now you get a decimal here, but we're talking people, so we don't want to have a part of a person. So when we're talking about people and population, we're going to just always round down here. Okay. All right, let's take a look at number 3. Similar idea. Make sure this is in focus here. Whoa, whoa. That did not help. Okay, there we go. All right, so in this case, we're going down, right? So a value of a car depreciates. That means it goes down by 12% each year. It loses value. It's not worth as much. So if we want to find the multiplier for a 12% decrease, we're going to do something similar to what we did in the last problem, but we're going to subtract, right? We want to take 100% of the value, and we want to subtract 12% of it. And when we're done with that, we're going to get 88% of the current value. So if we're decreasing by 12% every year, that means we're going to end up with 88% of whatever the previous value was. To get 88% of something, you just multiply it by 0.88 or 0.88. Okay, so that's how you find your multiplier or decay factor for a percent decrease. Right, percent decrease, you subtract the percent from 100 and then turn it into a decimal. For percent increase, like we did in the previous problem, you add your percent increase to 100 and then write it as a decimal. Okay, what is the value of the car after 1 year? Okay, so our initial amount was 40,000. Okay, and this is just 1 year, so we just have to multiply it by 0.88 to find out how much it's worth after the first year. And that is going to come out to be... Sorry, I have my notes here and I lost it. Oh, sorry, there it is. It's 35,200. Okay. All right, write an equation that will give you the value of the car after X years. Okay, so we're not going to go through the process of making a table again because I think we've already done that twice. But the idea is that every year that goes by, you have to multiply it by 0.88 again. So there's this repeated multiplication by 0.88. Right, after 3 years, you're going to have to multiply by 0.88 3 different times. So the idea here is that the value of the car, we'll do V for value, equals the initial amount, the initial value, or the value when 0 time had gone by. We're going to multiply by that decay factor, 0.88, and we have to do that X times, right? But repeated multiplication is represented by powers. So that's how we represent, multiple times. So in 20 years, the value of the car is going to be whatever that initial amount was, 40,000. We're going to multiply that by 0.88 to the 20th power. Okay, that's going to give us our value. So punch that into a calculator. You're going to end up with $3,102.51. Okay. So make sure that you can use a calculator to get that. Don't just take my word for it. I would practice with your calculator. Make sure you know how to do your exponents and you're not messing stuff up there. Because when you do it on your test, you're not going to have me to calculate it for you. So make sure you know how to use your calculator. Okay. From here, we're going to move into graphing. So let's take a look at the next two. When we graph these, we use a table, so we can do that here. You probably won't want to do that every single time, but let's go ahead and make that really quick. We'll just go real thorough here since this is going to help us review for your test. So I'm going to pick some values for x, and we're going to plug it into the function and see what we get. Okay, so I'm going to pick my favorite values here. These don't work all the time, but they'll work really good in this case. Let's start with 0. So if I put in 0 for x, then my function will be 3 to the 0 power, which we know is 1. Okay, if x is 1, I'm going to have 3 to the 1 power, because my function is 3 to the x, so 3 to the 1 equals 3. If If I have a 2 here, x is 2, then I'm going to have 3 to the 2. f of x will be 3 to the 2, or 9. Okay, so you can see this pattern of we're tripling, right? This is the growth factor. 1 times 3 is 3, 3 times 3 is 9. The next one will be 27, right? 81, and so on. Okay, let's look at it going backwards. So we got 3 to the negative 1 here. Okay, well, one of our properties of exponents are if you have a negative exponent, you push that guy down to the basement, right? And you get a fraction. So this is 3 to the negative 1 is 1/3. Okay, 3 to the negative 2 then would be it'd be 1 over 3 squared, which is 1 over 9. Okay, so notice the pattern, right? 1, 3, 9. 1, 1/3, 1/9. So they kind of like, these kind of almost, they're reciprocals of each other, right? And these guys right here are reciprocals of each other as well. 3 and 1/3, 9 and 1/9. So the next one is 27 over here, 1/27 over here, and so on. So when we graph this, we're going to have these coordinates, right? The first coordinate we have is 0, 1, because when x is 0, y is 1. We also have the coordinate 1, 3. We have the coordinate 2, 9, right? We have the coordinate negative 1, 1/3, and we have the coordinate negative 2, 1/9. So with those coordinates, we can get a pretty good idea of what this graph is going to look like. So let's jump up and graph them. So 0, 1, it's right here. Okay, 1, 3, 1, 3. Okay, and then 2, 9. 2, 9 is way up here. Okay, the next one would be 3, 27, but by then we're going to be like off the charts. So we're not going to be able to fit. 1, 2, okay, just make sure I have my scale right. So that should be 9. Yep, good. Okay, going the other way, we're going to have negative 1 and 1/3, which is going to be, somewhere over here. And then we're going to have negative 2, 1/9, and that's going to be almost impossible to see. So our graph is going to go up like this. Right, going to keep on going, keep on going, keep on going. Okay, so something like that. Couple key components here is that this is the y-intercept, right, at 0, 1, which is usually the case for these parent functions. And then we have an asymptote, right? This line gets closer and closer and closer to 0 without actually touching it. Okay. One of the other things I wanted to just point out really quick is in the previous problems we had like initial amount or a starting amount. Like we talked about the function, the general function looks like a times b to the x. So when you're looking at this one, you're like, well, what is the a? Where's a there? It would be 1, right? This is the same as 1 times 3 to the x. So if you're like, oh, yeah, okay, the initial amount is 1. Yeah, that makes sense. We're down here at 1. Okay, we start at 1, and then we're tripling. So 1, 3, 9, 27. Okay, going backwards, 1/3, 1/9, 27th, that kind of thing. So this is your initial amount, and this is your growth factor, or the pattern. You're multiplying by 3 every time here. All right, let's take a look at number 5. So this one, you should hopefully remember the relationship that these guys are going to have. This is 3 to the x, this is 1/3 to the x, so it's like a reciprocal, okay? We're going to see what it looks like, but hopefully this should ring a bell in just a second. So we're not going to do this for every single graph, but we're going to do it for the first couple just to be thorough here. And if you don't need this, you can, skip to the next video or fast forward or put me on like, double time playback or whatever you need to do. But I just want to make sure we have plenty of resources for you guys. All right, so this is a little bit different because we have, 1/3 to a power. So let's start with the 0 again, right? So we have 1 over 3 to the 1 power. If I put in a 0 for x, that'd be 1/3 to the 0 power. Oops, sorry, 0 power. Excuse me. 1/3 to the 0 power, excuse me. That's going to give us the number 1. Okay. All right, if x is 1, I'm going to have 1/3 to the 1 power, which is just 1/3. If I have a power of 2, right, put in x is 2, I'm going to have 1/3 to the 2, which is going to give me, that's the same thing as 1/3 times 1/3, right, which is 1 over 9. Okay. Going backwards is a little bit trickier. Let's take a look, though. So we have 1 over 3 to the negative 1. Well, remember, this gives me a fraction, right? Push it down to the basement. But what's going to happen is I'm going to have a fraction within a fraction. So I'm going to have a 1 over 1 over 3. How do we handle this? We multiply by the reciprocal. So 1 divided by 1/3 is the same as 1 times 3 over 1, which is just 3. Okay, next one, we have 1 over 3 to the negative 2. I'm going to go over here a little bit so we have room. So this is 1 over 1/3 squared, which is 1 over 1 over 9, which has to be 9, right? 1 divided by 1/9 is the same as 1 times 9 over 1, which is 9. All right, so the points that we have, I'm going to write them over here since I kind of ran out of room. If x is negative 2, y is 9, or f of x is 9. If we have x is negative 1, then the output of the function was 3, right? If x is 0, then the output is 1. If x is 1, the output is a third. If x is 2, the output is a ninth. Hopefully you see what's going to happen here because these are kind of like reversed. Let's graph it. 0, 1. Okay, cool. Well, that's the same so far. Nothing's really changed. Okay, let's do this. 1 comma 1/3. So 1 and then 1/3 up. That's going to be kind of hard to see. And then the next one, 2 1/9. That's even harder to see. 1/9 is real tiny down there. Then we have negative 1 3. So negative 1 3 right here. And then negative 2 9. One more. So, and then if we were to go further, negative 3 would be way up here, way up at like 27. Okay, so it's like coming down, and then we get closer and closer and closer to 0, but we never actually touch 0. Whoops, pencil broke. Okay, and that's kind of what our graph looks like. So what is the relationship between these two graphs? Well, this is like the backwards version of this, but to be more like specific, like mathematically, what we have is that this is a reflection of this over the y-axis. So if we wanted to compare this with the original, this is a reflection over y-axis. And that wasn't part of the question, but we're going to see that like later on, and so I just wanted to highlight that and say if you have 3 to the x and then you see the reciprocal 1 over 3 to the x, that is basically a reflection over the y-axis. Another way to write a reflection over the y-axis is to take your original function and make the exponent negative, right? So if I took this guy and I put a negative up inside with x, that's going to flip it over the y-axis. But if we rewrote this, 3 to the negative x, just like we talked about here, this is going to be 1 over 3 to the x. Right? Move that guy downstairs and make the exponent positive. But that's the same thing as 1 over 3 to the x power. So you can see that this and this are exactly the same, which is why this is a reflection over the y-axis. Okay. All right, I'm going to pause it there, and you guys can come back and we'll look at the next page. So this is page 2 of the exponential functions review.